So, today we are going to start the topics of velocity gradient, rate of deformation tensor, spin tensor, and then we will calculate the rate of change of volume as well as area. And finally, we will see one of the important theorems called the Reynolds transport theorem. Okay. So, remember velocity is a spatial vector, okay, which is shown here. Okay. So, consider you have a body at time t equal to 0, okay, and then you have a material element dx, okay, and as the body deforms and it occupies the current configuration at time t shown here. So, this material element maps to the spatial element dx. Okay. So, now as the body is moving, point P will have a velocity V p, and let this arrow show this velocity vector. Okay. So, the velocity of point P in the current configuration is V p. Okay. Similarly, the velocity vector of point Q will be V q. Okay. The direction of velocity at Q need not be same as the direction of velocity at P. Okay. So, we can draw a vector at Q parallel to the velocity vector at P, which is V p here shown by dotted line. Okay. Now, we can other way draw vector parallel to V q at point P, okay, which is shown here as dotted line. Okay. So, the relative velocity vector will be dV. Okay. So, the relative velocity vector between point P and Q will be given by dV. Okay. So, from the law of vector addition, okay, we know that the velocity V p plus dV will give you V q. Okay. So, the velocity of point Q will be velocity of point P plus the relative velocity vector dV between point Q and P. Okay. So, the gradient of velocity with respect to the spatial coordinates is now defined as the velocity gradient tensor, okay, and it is denoted by lowercase l, okay, and it is given by del v by del x, or in short you can write this as gradient of v, gradient of velocity. Okay. So, what does this velocity gradient tensor actually gives? So, it gives you the relative velocity of a particle, okay, which is currently at point Q with respect to a particle currently at point P, okay, that is dV equal to L dx. Okay. So, the velocity gradient tensor gives you the relative velocity of a particle at point Q relative to point P, okay, in the current configuration. Okay. Now, the tensor L, okay, and can be used to express the material time derivative of f as follows. Okay. So, f dot is del v by del x, this we already know. The material time derivative of the deformation gradient tensor is nothing but del v by del x. Okay. So, I can write del v by del x as del v by del x into del x by del capital X. Okay. Now, from equation number 87 on the previous slide, we can recognize that del v by del x is nothing but the velocity gradient tensor L, and del x by del x is nothing but the deformation gradient tensor F. So, I can write f dot as the velocity gradient tensor L times the deformation gradient tensor F. Okay. So, using this relation I can relate the material time derivative of the deformation gradient tensor with the velocity gradient tensor and the deformation gradient tensor. Okay. So, this relation we have to remember, because in later slides when we are doing some derivations, this will come very often. Okay. Now, coming to the next topic of rate of deformation tensor. So, you remember we have taken two material vectors dx1 and dx2 at point P, okay, and we had observed how these material vectors, okay, deform to spatial vectors dx1 and dx2. Okay. So, we know that dx1 is f dx1 and dx2 is f dx2. Okay. That we know. Okay. Now, let at time t, okay, the body undergo a small displacement u, which can be written as v into dt. Okay. Okay. So, sorry, this is du, a small displacement du, which is v dt. Okay. And let at time t plus delta t, the red dotted line which is here, okay, shows the configuration of the body at time t plus delta t. Okay. Now, so we had defined strain earlier and measured it as the change in the scalar product of two arbitrary vectors. So, we took dx1 and dx2 in the material configuration and we defined strain by how these material vectors deform, okay, how the scalar product of these two material vectors change, and that is how we came up with the concept of strain. Okay. So, for strain rate, now we have to define, okay, the rate of change of the scalar product of the material vectors. Okay. So, recall that we had derived as the scalar product of the spatial vectors is nothing but dx1, that is the material vector dx1 dotted with c times dx2, where c is the right Cauchy Green tensor and c is f transpose f. Okay. Now, taking the material time derivative on both the sides. Okay. We take the time derivative on both the sides, d by dt of dx1 dot dx2, and on the right hand side, since dx1 and dx2 are the material vectors, they are fixed, they are known. Therefore, we have dx1 dot c dot. Okay. So, the time derivative of the right Cauchy Green tensor. Okay. Now, we know that the Green Lagrange strain tensor E is 1 by 2 c minus I. Okay. So, which means that if I take the material time derivative of the Green Lagrange strain tensor, so I can write 2 E dot is equal to c dot. Okay. Which means I can replace c dot here with twice of E dot. Okay. I can replace the time derivative of the right Cauchy Green tensor with the time derivative of the Green Lagrange strain tensor, and that is what I am going to get. Okay. So, where E dot is called the material strain rate tensor. Okay. Because C is F transpose F, C dot will be, okay, because C is F transpose F, C dot will be F dot transpose F plus F transpose F dot. Okay. Which means the rate of Green Lagrange strain tensor E dot is nothing but 1 by 2 F dot transpose F plus F transpose F dot. Okay. Now, reversing, I mean alternatively I can express my material vectors in terms of the inverse of the deformation gradient tensor times the spatial vector dx1, and dx2 will be inverse of the deformation gradient tensor times dx2, okay, spatial vector dx2. Therefore, if I use this in equation 91, if I use this here, dx1 is f inverse dx1 and dx2 is f inverse dx2. What do I get? I get f inverse dx1 dot E dot f inverse dx2. Okay. Now, the first term in this bracket is a vector and this term over here is also a vector, and A dot B is A transpose B, where A is this quantity. Okay. So, I can write f inverse dx1 transpose E dot f inverse dx2. Okay. And I can open up the bracket, this bracket over here, and I can write dx1 transpose f inverse transpose E dot f inverse dx2. Okay. So, I can take dx1 out from the left hand side and dx2 out from the right hand side. Okay. And now, this whole expression over here is also a vector quantity, okay, because the term in the bracket here. Okay. So, the term in the bracket here is a second order tensor. So, second order tensor operating on a vector gives you vector, therefore, this quantity in the square bracket is also a vector. Okay. So, a vector transpose vector is nothing but vector dot vector. So, I can write this as dx1 dot f inverse transpose E dot f inverse dx2, and now I can denote this quantity in the bracket by symbol small d. So, okay. So, I can write dx1 dot d dx2. Okay. D is a tensor. I can show that this is a tensor. You know how to show something is a second order tensor. Okay. You have to use the transformation law. Okay. Now, this d is called the rate of deformation tensor d, and it is given by f inverse transpose E dot f inverse, and this is also called the spatial deformation tensor. Okay. Now, d can be treated as the push forward of the rate of Green Lagrange strain tensor. Okay. So, this is the symbol for the push forward operation. So, the push forward of the Green Lagrange strain tensor, that is E dot, is nothing but the rate of deformation tensor, and how this push forward is carried out, it is given by this particular expression f inverse transpose E dot f inverse. Okay. So, the pullback. Okay. So, the pullback of the rate of deformation tensor d is nothing but the rate of Green Lagrange strain tensor. So, E dot is pullback. So, this is the pullback sign of rate of deformation tensor, and how this pullback is carried out, f transpose d f. Okay. That is how you carry out the pullback of the rate of deformation tensor. Okay. Now, we can have a physical meaning, okay, or the interpretation of the rate of deformation tensor if we just consider dx1 equal to dx2 equal to dx. So, instead of taking two material vectors, we take one material vector and observe what happens to its length. Okay. So, let we consider a material vector dx given by dl into n, okay, where n is the unit normal along the vector direction, okay, unit vector along the vector direction, and dl is the length of the vector. So, this is what is your vector length dl. Okay. And now, this vector gets mapped to vector spatial vector dx given by dl into n, okay, where n is the unit vector along pq and dl is the length. Okay. So, d small l is the length of the vector pq. Okay. So, dx is dl into n. So, if we substitute this in our previous expression over here, okay, equation number 93, if we do that, what I will get? 1 by 2 d by dt of dx dot dx equal to dx dot d dx. Now, I know that dx is nothing but dl into n. So, this I can substitute in equation number 97. If I do this, okay, so if I do this, what do I get? Dx dot dx is nothing but dl square into n dot n, and n is a unit vector, therefore, n dot n is 1. So, we will get dl square. So, that is what you have it here. Similarly, on the right hand side you will get dl square n dot dn. Okay. Now, you can take the derivative of time derivative of dl square, it will be 2 dl into d by dt of dl. Okay. So, we take the time derivative and we get this. Okay. So, this 2 cancels out, and if we divide by dl square on both the sides, okay, if we divide by dl square on both the sides, then what do we get? We get 1 by dl d by dt of dl equal to n dot dn. Okay. Now, you can recognize that 1 by x d by dt of x is nothing but d by dt of ln x. Okay. This is a property. Okay. So, the derivative of logarithmic is 1 by x d by dt of x. Okay. So, this can be written as d by dt of natural log dn equal to n dot dn. Okay. So, what does rate of deformation tensor is giving you? It gives you the rate of extension per unit current length of a line element having a current direction defined by n. Okay. So, this is your, so d by dt dl, this is your rate of extension, okay, and 1 by dl will give you rate of extension per unit length. Okay. Okay. And this is for a line element whose current direction is along vector n. Okay. So, along vector n, okay, that is what it is giving you. So, sort of it is giving you the rate of stretch of the current line element, okay, dx. Okay. Now, what happens in case of rigid body motion? So, you know that in rigid body motion the body does not deform. Okay. So, the material vector dx will only rotate to dx, spatial vector dx, but the length of the vector will not change. And from if current position t to position configuration at t plus delta t, if there is a rigid body motion, then the length of the vector, spatial vector dx will not change. So, dl, okay, will not change, which means the material time derivative or the time derivative d by dt of dl, this quantity over here will be equal to 0. This equal to 0, okay, which means dl is constant. This would imply that the magnitude or the rate of deformation tensor is equal to 0 tensor, okay, which means there is no stretching involved. Okay. So, this has a physical implication, which means that under rigid body motions the body will not generate any strain. If there are no strains generated, there will be no stresses generated. So, this is physically intuitive, because if you just rotate a body, there will not be any stresses generated inside the body. So, if you have a strain measure, okay, for example, strain rate measure, for example, D, which gives you no change in the strain if there is a rigid body motion, then you will get physically no stress. If you derive your stress from D, you will get no stress, okay, increment in the stress, which is physically possible. Now, we can also briefly discuss an important concept of the Lie derivative. Okay. This is called the Lie derivative. So, you would have noted that the spatial rate of deformation tensor D, okay, is not the material time derivative of the Euler-Almansi strain tensor E. Okay. So, you would have noted that D is not equal to d by dt of E. See, the Euler-Almansi strain tensor is a spatial strain tensor and D is a spatial rate of deformation tensor, but the rate of E will not be equal to D. Okay. So, this important concept you have to understand. So, what is D? D is actually the push forward of the rate of Green-Lagrange strain tensor E, okay. And E is nothing but the pullback of Euler-Almanzi strain tensor, okay. So, D is nothing but the push forward of rate of Green-Lagrange strain tensor, okay, that we saw in the previous slides. Also, the Green-Lagrange strain tensor is nothing but the pullback of the Euler-Almanzi strain tensor E. Okay. This we saw when we were discussing Green-Lagrange and Euler-Almanzi strain tensor. Now, if I can write this as phi star d by dt of E. Okay. And what is E? E is this quantity over here. So, I can write E dot as d by dt of pullback of Euler-Almanzi strain tensor. I can substitute it here. I can say that D is nothing but the push forward of the material or the time derivative of the pullback of Euler-Almanzi strain tensor. Okay. So, this operation is called the Lie derivative of E. Okay. So, in general, if you have any tensor quantity G that goes over the mapping psi, then the Lie derivative of G is defined as, okay. So, this is a symbol for Lie derivative, okay, of the tensor G is nothing but phi star d by dt of phi star inverse G. So, push forward, okay, then material time derivative and the pullback. So, if you want to compute, and G is a spatial quantity, okay. So, this is a spatial tensor. So, if you have to take the material time derivative of a spatial tensor, then what you have to do? You have to pull it back to the material configuration, take the material time derivative and push it forward to the spatial configuration. Okay. So, first is pull back, then the material time derivative, and third push forward. Okay. So, Lie derivative constitutes of 3 steps: pull back, time derivative, push forward. Okay. So, next we come to the concept of spin tensor. Okay. So, we know that any second order tensor can be split additively into a symmetric part and a anti-symmetric part. So, the velocity gradient tensor L can be split into a symmetric part, which is rate of deformation tensor, and an anti-symmetric part, which is nothing but the spin tensor. Okay. Now, D is nothing but F inverse transpose E dot F inverse. This we have seen in our previous discussions, okay, on previous slides. And I can actually show that D is a symmetric tensor, which means D transpose is same as D. Okay. I can just take a D transpose here. Okay. D transpose will be F inverse transpose E dot F inverse transpose. Okay. So, this will be nothing but F inverse transpose E dot transpose F inverse transpose transpose. Okay. So, this is nothing but F inverse transpose, and now Green-Lagrange strain tensor is a symmetric tensor. Therefore, its time derivative also will be a symmetric tensor, which means E dot transpose is same as E dot. F inverse transpose transpose is nothing but F inverse, and this is nothing but the expression for D. Therefore, the rate of deformation tensor D is a symmetric tensor. So, once we have shown that D is a symmetric tensor, therefore, D is nothing but L plus L transpose by 2. Okay. If D is this, then W will be L minus L transpose by 2. Okay. So, W is called the spin tensor. Okay. So, this W is called nothing but the spin tensor. We will come to it why it is called a spin tensor. We will see why this name. Okay. So, why is W called the spin tensor? So, to show that, we first notice that the material time derivative of the deformation gradient tensor is the velocity gradient times the deformation gradient tensor. Okay. So, if f dot is LF, which means the velocity gradient tensor is f dot f inverse, which means L transpose is f inverse transpose f dot transpose. Why we are doing this? I mean, we know that W is L minus L transpose by 2. So, this is our L here and this is our L transpose. Okay. And because W is 1 by 2 L minus L transpose, and I can substitute these two quantities here. Okay. Then what I get? W is f dot f inverse minus f inverse transpose f dot transpose by 2. Okay. Now, again what I can do? I can use the polar decomposition theorem. I know that for right polar decomposition, f equal to r into u, where r is a orthogonal tensor, u is a symmetric tensor, which is also called the right stretch tensor. Okay. So, if f equal to r u, then f dot will be r dot u plus r u dot. Okay. So, this I can substitute, I can compute f dot transpose here. Okay. And I can substitute both f dot and f dot transpose in terms of r and u in equation 109. Okay. I can substitute these here and then I will get following expression. Okay. I am getting this following expression. There is this whole bracket and this is this bracket over here. Okay. So, this is your f dot transpose and this is f dot. Okay. Now, I can take f inverse inside. I can open up the bracket. I can take f inverse transpose here inside and I can write following expression. I can write this expression. Seems like a very long expression, but we will quickly see how it comes to a very nice small expression. Okay. So, we know that f is r u, which means f inverse is u inverse r transpose. Okay. Because r is a orthogonal tensor. So, f inverse is u inverse r inverse, and since r is a orthogonal tensor, r inverse will be equal to r transpose. That is what we have written over here. Okay. Now, f inverse is u inverse r transpose. So, I can substitute f inverse here. Okay. I can substitute f inverse here. Okay. So, f inverse transpose is r u inverse. Okay. Let me just erase this part. So, from here I can compute f inverse transpose and I can substitute f inverse transpose here and here. Okay. In terms of r and u. If I do this, I will get r dot u u inverse r transpose plus r u dot u inverse r transpose on the as the first term, and r u inverse u r dot transpose plus r u inverse u dot transpose r transpose as the second term. Looks like a very big expression, okay, right now, but I can rearrange. So, what I can do? I can see, okay, see the other thing you have to notice this is u u inverse is nothing but identity. Okay. So, u u inverse here is nothing but identity. Okay. And then if I put identity, I will get equation 114. Okay. Now, what I can do is little rearrangement. I can bring this term over here, the first and the third term inside one bracket, and I can bring the second term and the fourth term inside second bracket. Okay. So, if I do this, I can write the spin tensor as this first term which does not have any u, and the second term which is contains all the u's or the right stress tensors. Okay. Up till now we are fine. Now, what we do? Okay, I can take R outside the bracket from the left hand side, and R transpose. Okay, so, this I can take out from the left hand side, and R transpose I can take outside from the left hand side. So, what I am left with is in the second term this quantity, okay, R into u dot u inverse minus u inverse u transpose u dot transpose R transpose. Now, I know that R transpose is identity, okay, because R is a orthogonal tensor. So, R inverse is identity, R inverse is R transpose, therefore, R transpose is identity. If I take the time derivative, I get R dot R transpose plus R dot transpose equal to 0 tensor. Okay. So, I can write R dot transpose as minus of R dot R transpose, and this I can use here. Okay. If I use that here, I will get W is R dot R transpose plus the second term. Now, as a special case, if you have rigid body motions, in case you have rigid body motions, what it means is that the stretch tensor will be equal to the identity tensor. Okay. So, there will be no stretch, which means u equal to I, okay, because f is I, and then u will become I, which means u dot will be equal to 0. Okay. So, if u dot is equal to 0, it implies u dot transpose is also equal to 0 tensor. So, this I can use here. Okay. This I can use here. So, for rigid body motion, I can show that my spin tensor is nothing but the material time derivative of the rotation tensor times the transpose of the rotation tensor, okay, R dot R transpose. There is no stretch here. So, only rotation is involved. So, that is why omega is also called the spin tensor, because as a special case I can show it is composed only of spin or the rotation. Okay. There is a time derivative, therefore, the rate of rotation is the spin. So, it is also called the spin tensor. Okay. So, I can attach some physical meaning to it. Okay. So, often this spin tensor can be physically interpreted in terms of its associated angular velocity vector omega. Okay. So, the spin tensor omega is nothing but 0 minus omega 3 omega 2 omega 3 0 minus omega 1 minus omega 2 omega 1 1, oh sorry, this is 0, okay, where omega is the spin vector, okay, angular velocity vector, okay, this is the component. So, you can interpret this as, if you have a point P, okay, and the angular velocity at this point is omega, then and you have this point Q whose position vector with respect to point P is dx, okay, then the relative velocity vector dv of Q with respect to P is dv, then dv is nothing but omega cross dx, or you can show it also is same as the spin tensor times spatial vector dx. So, the spin tensor maps the relative spatial vector dx to the velocity vector. Okay. So, omega maps, okay, relative position vector dx to the relative velocity vector dv. Okay. So, the angular velocity vector omega is also called the axial vector corresponding to the spin tensor w. Okay. Now, next we come to computing the rate of change of volume and areas. First, we look into the rate of change of volume. Okay. So, we had earlier derived that Jacobian is equal to determinant of f, that is determinant of the deformation gradient tensor. Okay. So, Jacobian characterize the volume change. Okay. Now, if we take the material time derivative on both the sides, okay, if I take the material time derivative on both the sides, okay, which means d by dt of j equal to d by dt of determinant of f, and that is what I have shown in equation 122. So, d by dt of j is nothing but j dot equal to d by dt of determinant of f. Okay. So, d by dt of determinant of f. Okay. So, let us say determinant of f is a scalar, say x, okay, and x is a function of f. Okay. So, d by dt of determinant of f equivalently I can write as d by dt of x, where x is a function of f. So, using chain rule I can write dx by df into, now dx by df is a second order tensor, and now our final quantity, see on the left hand side we have a scalar. So, dx by df is a second order tensor. To make it a scalar, I have to take a double contraction. Okay. So, I take dx by dx into d by dt of f. Okay. So, that is what we have shown here. Okay. So, this is our x, okay, and d by dt of f is nothing but f dot. Okay. So, j dot is nothing but d by df of determinant of f double contracted with the rate of change of deformation gradient tensor. Okay. Now, if you look closely this first term, now let me rub this. If you look closely this term, okay. So, this is nothing but you have to find out the derivative of determinant of a tensor with respect to its component. Okay. And if you can recall from our discussion when we are discussing the mathematical essential for this course, that the derivative of the determinant of a second order tensor with respect to the tensor components is nothing but determinant of the second order tensor into F inverse transpose, the inverse transpose of the tensor itself. Okay. So, d by dA of determinant of A we had showed is nothing but determinant of A times A inverse transpose. So, this we had derived. Okay. So, this I can write, and determinant of f is nothing but Jacobian. I can write this as Jacobian times F inverse transpose double contracted with f dot. Okay. And now, f dot is nothing but velocity gradient tensor times the deformation gradient tensor f. So, f dot is LF, I can substitute and I can get J F inverse transpose double contracted with LF. Okay. Now, I can use this identity that a second order tensor contracted with a product of two second order tensor B and C is nothing but B transpose A double contracted with tensor C. So, if I use this here, I can show that the rate of change of Jacobian is nothing but J F F inverse double contracted with the velocity gradient tensor L. Okay. And what is F F inverse? Okay. So, F inverse is nothing but identity tensor. Okay. So, this is nothing but identity tensor. Okay. So, the rate of change of Jacobian, okay, is nothing but J and I contracted with the velocity gradient tensor L. Now, L is nothing but gradient of V, that we have seen. Okay. L is nothing but gradient of V. So, I can also write this expression as J I contracted with gradient of V. Okay. And we saw that I contraction, let me write L. Okay. So, the double contraction of a tensor with respect to identity tensor is nothing but the trace of that tensor. Okay. So, I can write this expression also as J trace of L, J times trace of velocity gradient tensor. Now, L is nothing but D plus W. The velocity gradient tensor can be split into the deformation gradient and the spin tensor. Okay. Now, I can open up the bracket and I can write J dot as J times trace of D plus trace of omega. Okay. So, now you know that D is a symmetric tensor, omega is a anti-symmetric tensor. So, the trace of an anti-symmetric tensor is nothing but 0. Okay. Trace of a anti-symmetric tensor is 0, which means I can write J dot as divergence of u. Okay. So, this expression over here. Okay. So, let me rub this. So, I contracted with gradient of a vector quantity is nothing but equal to the divergence of that quantity. So, J dot is nothing but J divergence of V, which is nothing but equal to J trace of L is nothing but equal to J trace of T. Okay. So, with this we come to the next topic, which is rate of change of area. Okay. So, now you have an infinitesimal spatial area element dA, and now you want to compute the rate of change of that area. Okay. So, we know from Nelson's formula, okay, that the spatial area vector dA is nothing but J F inverse transpose times the material area element d capital A, or I can write N dA is equal to J F inverse transpose capital N d A. Okay. Now, if I take the material time derivative on both the sides, if I take the material time derivative on both the sides, I can write d by dt of dA is equal to d by dt of J F inverse transpose d capital A. Now, d capital A is a constant quantity, it can be taken out. Okay. So, now I can open up the brackets here, I can take the time derivative inside the bracket and I can write J dot F inverse transpose plus J F dot inverse transpose. Okay. So, from our previous slides we know that J dot is J divergence of V equal to J trace of L equal to J trace of D. Okay. So, I can substitute for J dot from here, and then I also know that F inverse is identity, which means I can show that if I take the material time derivative here, I can show that F dot inverse is same as minus of F dot F inverse. Okay. So, if I use this both of them, okay. So, from here F dot inverse is nothing but this kind of quantity over here, and now I can substitute J dot here. I can further simplify F dot inverse. So, we know that F dot is LF. So, F dot inverse Okay. So, f dot inverse. So, this f dot is nothing but LF. So, I can have f dot inverse is minus of f inverse LF f inverse. Now, f inverse is nothing but identity, therefore, f dot inverse is nothing but minus of f inverse L. Okay. So, I can substitute this expression over here. So, I can show then that the rate of change of spatial area element dA is nothing but J divergence of V f inverse transpose plus J f dot inverse transpose, okay, where then if I put f dot inverse transpose from our previous slides, okay, which we derived here, I get following expression. Okay. Now, I can take Jacobian outside and f inverse transpose outside the. So, J is common in both the expressions and f inverse transpose is common in both the expressions. So, I can take out J and f inverse transpose outside the bracket and I can write d by dt of dA as divergence of V minus L transpose J f inverse transpose dA. And what is J f inverse transpose? From Nelson's formula we know that this is nothing but the spatial area element dA. Okay. So, I can write dA here. Okay. If I write that, I can show that the rate of change of spatial area element dA is equal to divergence of the velocity vector minus the transpose of the velocity gradient tensor times the spatial area element dA. Okay. Last, we come to the topic of Reynolds transport theorem. Okay. So, this is the last topic in kinematics that we discuss, and then we will discuss few examples, solved examples to complete this topic of kinematics. Okay. So, Reynolds transport theorem is a very important theorem. Okay. So, it relates the material time derivative of the spatially integral of spatial quantities. Okay. So, till now you would have observed we were dealing with time rate of change of continuum fields. Okay. Now, what we consider is the rate of change of integral quantities. Okay. How do you calculate the material time derivative of integral of spatial quantities? Okay. Now, consider you have an integral I of the field G, which is given by G x comma t. So, it is a spatial field, it depends on the spatial coordinates x and over the body B, say at time t. Okay. Now, this is the integral. Okay. I is integral over the volume G of x t dV. Okay. So, integral of B is nothing but the triple integral. Okay. So, and dV is nothing but dx1, dx2, dx3. Okay. Now, if I take the material time derivative on both the sides, okay, if I take d by dt of I, which is nothing but I dot. So, on the left hand right hand side I will have d by dt of this integral quantity. Okay. Now, the problem is now I cannot take this derivative time derivative inside the integral sign. Why? This is because my current volume, okay, the current configuration corresponding to the current volume is not known. Okay. Now, if it is not known, it depends on time, then I cannot take this derivative inside. So, how can you evaluate this? So, to evaluate this, what we do is use this relation, okay, the relation between the volume elements in the spatial and the material configuration. So, dV is J dV 0. Remember, I mean, to be clear, earlier we were using small dV and capital dV for the material volume element. Here I am using dV and dV 0. Okay. And also, using the deformation mapping, okay, x psi comma t, you can convert g x comma t to another function g bar psi x comma t. Okay. So, g and g bar are the same function, but one is expressed in the material coordinates, the other is expressed in the spatial coordinate. Okay. So, if I substitute dv here and if I use this here, I have transformed the integral over the current volume to the integral over the reference volume or the material description, okay, or the material volume. Okay. So, I dot is nothing but d by dt of integral over the initial volume g bar x comma t and j dv 0. So, this is your j dv 0. Now, I know my material volume. I can now take this differentiation with respect to time inside the integral sign, because now I know the configuration, material configuration. So, I can take the differentiation with respect to time inside the integral, and then I can write, and I have to take the, so I have to take the time derivative of this integrand g bar j. So, the time derivative of g bar j is nothing but g bar dot j plus j bar j dot, okay, g bar j dot. Okay. Now, from our previous discussions, we know that j dot is nothing but divergence of v. Okay. This is trace of t. Okay. So, j bar is nothing but j times divergence of v. So, if I use this, okay, I can write g bar dot j plus g bar j divergence of v times dv 0. Now, I have, see, now I have Jacobian, okay. Both the terms have Jacobian. So, I can take the Jacobian out from the right hand side, okay, here, and then I can write g bar x comma t as g of x comma t. They are one and the same. Okay. So, using this I can derive, okay. So, g bar is g, therefore, g bar dot is nothing but g dot, and this j dv 0 is nothing but dv. Okay. So, I can write the first term here becomes g dot and this becomes g, and then you have divergence of v, okay, and j dv 0 becomes dv, and this integral over the reference volume becomes integral over the current volume. Okay. So, now I have the expression for the material time derivative of the integral of a spatial quantity over the current volume, okay, and this is given by expression shown in equation 130, and this is called the Reynolds transport theorem. Okay. This is a very important theorem. Okay. It helps you to carry out the material time derivative of an integral of a spatial quantity over the current volume. Okay. Now, I can relate the, I can get more physical interpretation of this expression 130. So, what from our previous discussion on how to compute the material time derivative of a spatial quantity, we know that the material time derivative of the spatial quantity g will be nothing but del g by del t, keeping x fixed, okay, plus the gradient of g times the velocity vector. Now, if I use this here, what do I get? I get del g by del t plus the gradient of g times velocity plus g times divergence of u. Okay. Now, these, if I look into this term over here, this term is nothing but, okay, if I just drop x comma t, I can neatly write like this. It is the same expression, but just x comma t has been removed, and this second expression is nothing but divergence of g into v, okay, and the first term remains there itself. Now, in the second term over here, I can split into two, one term plus the integral of a divergence term, and now I can apply Gauss divergence theorem. I can convert this volume integral over here to an integral over the surface area. Divergence of g v over d v will be nothing but the integral over the surface g v dot n dA. Okay. Therefore, I have split I dot into two, one over the volume and the other over the surface. So, the total rate of change of I is nothing but the rate of production of G inside the body. Okay. So, del G by del T is the production of G at a point, current spatial position x, okay. And then when you take the integral over the volume, you get the total rate of production of G inside the body, plus you have the second term which shows that this is nothing but the net transport of the quantity G across its boundary. Okay. So, I dot is nothing but, so the Reynolds transport theorem gives you nothing but the rate of production of G inside the body plus the transport of G across its boundary. Okay. So, with this we have covered all the essentials of kinematics which is required for this course. So, next we will do few examples.